Hey there, in this recording I'm going to describe streamlines in fluids inside a containing object. I'm going to describe how we can do a very simple experiment to understand how those streamlines work. The apparatus I have, I've just placed it inside a bath. It's just a regular metal cooking pot or mixing pot that you could get anywhere. What I have here is just tap water, just regular tap water, and in the bottom of it here I have I took a tea bag, standard tea bag, and I took out the tea leaves. So what you see in there are tea leaves, and that's just the color of the tea mixing in with the water. Now the purpose of this lecture is to describe a few simple ideas. This is part of what I call the skunk works lectures. The idea is that we want to tap into the force of a fluid in order to effect lift. We don't currently achieve, in modern physics, we don't do it this way. The way we currently do it is we have like a plane wing moving through the air, affecting some kind of pressure differential, and then the wing achieves lift. The other established way of doing it is you put fuel into the base of a rocket and it lifts. The proposed idea here, theoretical idea here, this is part one of the two-part lecture. In part one I describe the way the fluid moves inside the surface. We're not so much concerned with achieving or attempting to achieve some form of weight loss. We're actually more interested in understanding how the fluid behaves when it's spinning. So it's a simple setup. This is going to be the kind of apparatus I'll use later. It's just a regular mixing pot, water. That will be the chosen fluid for the next experiment. The tea leaves are just here to try and demonstrate and highlight the way the streamlines are flowing. Now here's the thing, a spinning fluid inside a circular object has actually been explored by quite a few people over the years. When Newton described his Principia, he worked on spinning objects. He didn't focus so much on fluids, but he focused on objects spinning in circles. The rule is pretty simple. If you spin something and you move out to the edges, you get a change in acceleration. So the acceleration increases and then decreases to zero in the center. And it's a very simple formula. It's A is equal to v squared over r. So you've essentially two forces. You've at right angles moving around. The container pushes the water in and the water goes around, and therefore he derived A, which is the acceleration, is v squared over r. So the really important point to note is that this is the reverse of a gravity field. So if you think of something falling to the earth, let's just imagine this is the edge of the planet and it falls in. Well, we know that we accelerate as we fall to the center of the earth. Now if we spin this water, the acceleration is out. It's an outward acceleration, and this way, so it's a tangent. So the rule is A is equal to v squared over r. So this is a really powerful system for accelerations. It's not, people don't traditionally teach spinning fluids and accelerations and producing force. Mostly we focus on Bernoulli, and we focus on A is equal to v squared over r, and we tend to have solid surfaces. So in this case here we're dealing with a fluid, so we have to add in the concept of a streamline, and that is the fluids forming these lines, what are called streamlines, moving inside the fluid, and they all individually combine to produce the overall motion of the fluid. That's streamlines. So we're going to talk about how the streamlines work first. We're going to try and understand how the fluid behaves when you accelerate it and then I'm going to let it decelerate, and we're going to see how it works. Now, another very interesting thing to note about this is when Einstein first worked on general relativity, he did not work on the planets. His idea was to apply general relativity to a bucket of water. And he spent quite a number of years with a friend of his working on the mathematics for, say, a bucket of water, because he realized that this is the opposite effect of a gravity field, and it's also a series of accelerations as you move out. So as you move out, the acceleration grows and grows and grows and grows and grows. And he said, well, therefore it must generate gravity waves, and maybe I can mathematically model it. And he attempted to do that, and he failed. And he sat on general relativity for an awfully long time, and then he realized he could apply it to the orbits of planets. And he did one very famous experiment where he predicted the orbits of planets, and he proved general relativity worked, but he couldn't get it to work with this. So therefore, general relativity is about really big stuff. It's about the planets and all that good stuff. And then this got left behind because the gravity waves it generates and so on, they're almost negligible. I'm not talking about gravity waves to produce lift. The force isn't strong enough at all. But so the lift I'm talking about is actually classical lift, and it's actually surprisingly straightforward. When I show you the idea, it's actually fairly logical. There's no fancy science involved. There's no weird forces. It's just kinetic energy and redirecting kinetic energy. That's all it is. So for now, we just focus on the liquid and the tea leaves, just to try and help you see the position of the streamlines. The tea leaves will be carried inside the moving frame of reference, and there will be a higher acceleration at the edge, and it will be less at the middle. So what we will see is as I accelerate, we will see the water moving out from the center, coming out to the edges and pushing up, and the tea bags moving through with the streamlines. It'll be a little bit chaotic, but what I want to do is show you 2 points: acceleration and then deceleration. And that's mostly what I want to record, and I have a diagram to show how it works, and then we come to the conclusion of how can we tap into this, possibly to produce some form of lift. It's theoretical. I'll show a little simple rig I have in place. It doesn't produce lift, but it produces weight loss. But this is first experiment. First, let's just first understand this before we move to the next level of understanding. So I'm going to take just a fork. I'm just going to spin it. I'm just going to spin this water around, right. Now we could imagine replacing this fork with a motor and a paddle, which I'll do in the next experiment. But let's just spin it around. You'll notice that the water is evacuating the center point. It comes up at the edges. It's all pretty intuitive. There's nothing fancy going on here, right? So this is water being accelerated, right? The shape is the center is evacuated, and the edges rise. Okay. So I'm going to let it decelerate now. So this is the part of the water which is moving the fastest. There's the highest level of acceleration. The fluid is decelerating. It's returning back. It's being reclaimed by the gravity field. There's the potential is pushing the water down, and the edges of the objects are slowing it down. Now I want you to concentrate in here. Concentrate into the center. I'll just get rid of those bubbles. Concentrate into here. And what you're going to see is that the tea leaves are all going back in. They're all heading back in. Heading back in there. All one after the other, heading back in there. And they're not remaining mixed into the liquid. Right? So basically, the point of this experiment is to show the streamlines. the streamlines are going back in, going back in, going back in. But when I initially spun it, they went out. But they're like almost every single tea leaf is going back in, almost every single one, and they're returning to form a perfectly geometric shape. And the reason that happens is it's a bit like the orbits of planets. The mechanics of our reality are very precise. Although you might have a chaotic fluid moving, the individual particles follow very definite paths. So if we take a look now, you can see it's almost returned exactly to where it was. And you can run this experiment yourself at home. It's really simple. Now, the next thing to understand is what's going on and how can we understand it and then hopefully take advantage of it. So the idea would be, if I was to draw this on a piece of paper, what we have is we have the container, and we have the water being spun around, which you just saw, and that's good, all good. And then we have the point at which the water slows down and is at rest, which is in here, and that's what we just saw. It forms a nice a pattern in the center again, which we can see right there. But here's the more interesting thing, right? Although the water is spinning around like this, right, which is with, you know, I spun it, and the water was going around, what was happening was that the streamlines, although they're moving around, they're moving up when they accelerate, and they're moving at the edge of the container, up at the edge of the container. And then when they begin to decelerate, the fastest moving streamlines push out the slowest ones, and the slowest ones come in, right? So when I'm spinning it with the fork, what's actually happening is it's like a butterfly effect, a butterfly wing effect. Yeah, the water's going up. The tea particle is gaining height in terms of the, let's call this the XY plane. On an XY plane, ignoring Z, the tea leaf goes up and up and up and up and up and up and up, and then the streamline that it's in decelerates and it goes back down, and then you accelerate it again and it goes up. So what's actually happening inside a container shaped like this is it's pushing up and decelerating and pushing down, and it's pushing up and it's pushing down. Now, the idea in the next lecture will be, let's see, can we take advantage of this kinetic component, and this uplift, it's not strong enough. It's not strong enough to produce lift for the object, right? So we're going to have to make some amendments to this object. Yeah, we're going to have to make some amendments to this object to make the water go up in a stronger way. Don't forget that according to the Newtonian mechanical laws, A is equal to V squared over R. So what we have is the largest amount of acceleration out here, the least in here, and it's evacuated. But always be thinking about the streamlines. The streamlines are that the liquid goes around and it goes up and it comes back down, up and back down. So this is part one of the PySpace Skunk Works lecture, and we're going to see, can we effect some kind of, I won't say